Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Welcome to our presentation. We start today in a futuristic yet familiar cityscape where information is everything. In the heart of the city, there is a powerful controlling force known simply as the generator. This master intelligence holds an immense knowledge base, knowing everything that has ever transpired. But there is a crucial flaw. Its memory is frozen in time. It is a static mind, perpetually stuck in the moment it was trained. This presents a massive challenge in our rapidly evolving world. When we ask this intelligence novel questions or seek information about recent events, the stakes become incredibly high. The generator doesn't consciously lie, instead, it hallucinates. It confidently fabricates plausible sounding, yet entirely false facts because it lacks the necessary context or updated information. Look at the critical warning displayed. System failure, critical hallucination detected, data integrity compromised. This is the outcome when we rely on unchecked knowledge. A single, convincing hallucination can lead to catastrophic business decisions, regulatory failure, or a complete loss of trust, bringing an entire technological empire to its knees. Our mission is to solve this core problem of trust and ensure that the powerful intelligence we rely on is always grounded in verifiable truth. The truth, right now, is a ghost in the machine. When the core memory fails, when the primary intelligence starts fabricating its own facts, you don't call engineering for a deep system overhaul. You need an investigator, a specialist who can reconstruct the facts from the ground up. You need a detective. Meet RAG, Retrieval Augmented Generation. RAG is the expert specialist called in when the generator's testimony cannot be trusted. RAG operates under a completely different philosophy than traditional AI methods. He doesn't try to surgically reprogram the witness, attempting to alter the fundamental LLM or retrain its entire knowledge base. That process is far too costly and slow. Instead, RAG acts as a meticulous detective. He builds a case completely from the ground up, based on external, verifiable evidence. He recognizes that the large language model is an incredible reasoning engine, but it is not inherently a fact-checker. The RAG framework provides the facts and then asks the LLM to simply reason upon them. RAG ensures that every conclusion drawn, every output generated, is based on one thing and one thing only: evidence. Every robust investigation begins by establishing the facts. Our detective starts his work at the city archives, which we call the knowledge base. For RAG, the evidence is the organization's proprietary data, the treasure trove of documents, manuals, and records that hold all of the institutional intelligence. This data comes in two crucial forms. First, we have unstructured data, which includes all the long-form text documents like PDF manuals, crucial conversation logs from customer interactions, and internal reports. Second, we have structured data, which encompasses highly organized information such as SQL tables and critical configuration data found in JSON files. All of this information forms the foundation of the case. However, simply possessing the evidence is not enough to solve the case efficiently. As noted in the case file, there is a fundamental problem. The generator, our large language model, has a context window limit. We cannot simply hand it a massive 5,000-page manual and expect it to quickly pull out the relevant detail. The LLM's memory for context is limited. Therefore, this mountain of evidence must be systematically broken down into smaller, digestible chunks and processed before it can become truly useful and actionable for our investigation. To bridge the gap between human language and machine intelligence, RAG employs a universal translator. We call this critical piece of the puzzle the forensic linguist, which is the embedding model. Human language is inherently ambiguous, filled with nuances, idioms, and contextual meaning that machines struggle to parse. Machines thrive in the rigid, quantifiable world of numbers. The embedding model is a highly specialized neural network designed to solve this translational problem. RAG takes a piece of evidence, a chunk of text from the knowledge base, and feeds it into this model. The embedding model then reads and interprets the entire semantic meaning of that chunk. Crucially, it converts that meaning into a vector, which is a unique set of coordinates in a high-dimensional mathematical space. This process moves beyond simple keyword matching, which is often brittle and inaccurate. Instead, it captures the deep, underlying meaning of the text. As the concept explains, it is the difference between blindly matching the word canine and truly understanding the abstract idea of a dog. This powerful numerical representation allows RAG to find highly relevant conceptual matches, even if the source documents use entirely different vocabulary than the user's query. Once the text has been translated into numerical vectors, every piece of evidence receives a specific location on the map, which we call the semantic vector space. This visual representation helps us understand the power of the embedding model. The model does not assign random numbers to documents. Instead, it places concepts with similar meanings physically close together in this conceptual city map. If you look at the clusters on the map under the animals section, concepts like kitten, cat, and feline are tightly grouped neighbors. Similarly, under technology, you find laptop, computer, and screen clustered together. This proximity is the entire basis of RAG's search capability. For instance, if you were to vectorize the word dog, its vector would land directly adjacent to the vector for canine because they share near identical semantic meaning. Conversely, an unrelated concept like banana would be placed in a completely different, distant part of the city, nowhere near the technology or animal clusters. This intelligent placement allows us to search by concept, not just keyword. For a quick technical note, while this map is visualized in simple 2D for illustrative purposes, a typical production vector, such as Google's modern text embedding models, operates with 1,536 dimensions. This incredibly high dimensionality creates an incredibly detailed and nuanced map of meaning, capable of capturing highly complex relationships between documents. With millions of vector-encoded clues now processed, the next crucial step is storing them efficiently for rapid retrieval. If we tried to search through these vast quantities of vectors using a simple one-by-one method, often called brute force, the process would be far too slow for any real-time application. The case would metaphorically go cold. We need a specialized system for storing the evidence, the vector database. A vector database is a highly optimized warehouse engineered specifically for one primary task: similarity search. Unlike a traditional relational database, the vector database is built from the ground up to index and manage multi-dimensional vectors. This unique architecture allows it to immediately identify and locate the nearest matching evidence, the closest vectors to a new query, in milliseconds. This instantaneous capability is the technological engine that drives RAG and allows it to function in real time. Without the speed provided by a specialized vector database, the augmented generation process would be impractical. If you are exploring implementing RAG in a production environment, you might come across common names for these high-performance vaults, which include industry leaders such as Pinecone, Milvus, and Weaviate. The core innovation that allows the vector database to perform lightning-fast similarity search across potentially billions of documents lies in its indexing algorithms. We are talking about the express train to the truth, HNSW indexing. HNSW stands for Hierarchical Navigable Small World, and it is the standard mechanism used to perform Approximate Nearest Neighbor, or ANN, search. HNSW organizes the vector data into a hierarchical graph, structuring the entire semantic map into multiple layers, much like a subway map with express lines and local routes. This efficient structure prevents us from having to check every single document. The process begins on the highway, the top layer of the index. When a search is initiated, the system starts on this high-level graph, which connects widely distant conceptual neighborhoods. This allows RAG to quickly jump across the entire data set, landing directly in the right neighborhood of meaning relevant to the query. Once in the correct area, the search transitions to the local streets, the bottom layer. This layer is much denser and more granular. Here, the system performs a refined, detailed search to pinpoint the single exact piece of evidence needed. By layering the index, HNSW minimizes the number of data points RAG needs to examine, enabling instant retrieval and making it possible to work with evidence derived from trillions of tokens of information. Now we introduce the operational bridge between the user's question and the evidence vault, the retriever. The retriever serves as the search warrant, the component that dictates what evidence is necessary to answer the case. Its mission is critical and follows 3 distinct steps. Step 1 is to embed the query. When a user asks a question, for example, what is RAG's main function? The retriever takes that plain text question and translates it into a vector using the exact same embedding model that processed the original evidence. This consistency is essential to ensure the query vector lands in the correct position on the semantic map. Step 2 is to execute search. The new query vector is immediately sent to the vector database, which utilizes HNSW indexing to rapidly identify the most relevant pieces of evidence. Step 3 is rank and return. The retriever then retrieves the top K most relevant chunks of text. In our example, this might be the top 5 closest semantic matches. These documents are returned along with a relevance score, indicating how closely each piece of evidence matches the original query. The retrieved evidence is the raw material that the LLM will use to formulate a grounded and accurate response. A truly modern detective knows that relying on just one tool is often insufficient for complex cases. Sometimes, semantic meaning alone is not enough to find the exact piece of evidence needed. For instance, if you're searching for a highly specific serial number like XJ900, or a proper name, vector search can sometimes miss these precise lexical matches because they lack deep semantic neighbors. This is why modern retrievers utilize hybrid search, a method designed to obtain the best of both worlds. Hybrid search intelligently blends 2 distinct search methodologies. The first is dense search, which relies on our vectors and the embedding model to understand the semantic meaning and the user's underlying intent, such as, how do I reset the device? The second method is sparse search, which relies on traditional keyword matching and indexing to find exact terms, like the specific XJ900 serial code. The retriever's job is to blend the results from both the dense and sparse searches, weighing their relevance appropriately. By combining conceptual understanding with precise keyword matching, RAG ensures that absolutely no clue is missed, guaranteeing the most comprehensive and accurate retrieval possible before the information is sent to the generator. We have now reached the final and most critical phase of the RAG pipeline, the interrogation, which is achieved through augmenting the prompt. RAG understands that the generator, the large language model, is prone to hallucination if left to its own devices. Therefore, RAG never asks the generator what it thinks or relies on its internal training knowledge. Instead, RAG presents only the verified, retrieved facts and then asks the model for a conclusion based strictly on those facts. This is the heart of augmentation. Look closely at the comparison here. The standard prompt is simple. User, how do I fix error 504? The LLM would answer based on potentially outdated or vague training data. The augmented prompt is fundamentally different. RAG first injects a strict system instruction. Use only the context below to answer the user. It then inserts the verified context, which was retrieved from the vector database. Error 504 indicates a gateway timeout. To fix, restart the Nginx service. Finally, the user question is presented. By injecting this highly relevant, verified context directly into the prompt, RAG effectively handcuffs the LLM, confining its response space and eliminating its ability to hallucinate or wander off script. This controlled environment ensures accuracy and relevance. The successful application of Retrieval Augmented Generation culminates in the verdict, grounded generation. This slide shows the dramatic difference RAG makes. On the left, we see the output of the generator before RAG intervention. It is chaotic, spewing confident but utterly fabricated nonsense about server ghosts, quantum flux capacitors, and system failures. This is a classic hallucination. We must remember that the generator, the LLM, is a powerful synthesizer, excellent at constructing coherent language, but it is not inherently a fact checker. Its greatest vulnerability is being fed bad or contextless information. Now look at the output after RAG on the right. The answer is concise, accurate, and completely grounded in the evidence provided. Error 504 indicates a gateway timeout. To fix, restart the engine X service. By providing verified, relevant context directly in the prompt, RAG forces the generator to base its testimony entirely on verifiable evidence. The result is an answer that is truthful, accurate, and most importantly, citable. Notice the bracketed references. These links tie the statement directly back to the source documents. The principle is simple yet profound. We replace the risk of hallucination with the certainty of documentation. We have shifted from garbage in, garbage out to evidence in, truth out, creating a reliable source of information. To truly appreciate the RAG framework, it is essential to compare it to the traditional method of improving LLM knowledge, fine-tuning. Fine-tuning is often described as the back-alley brain surgery. This process involves rewriting the LLM's core knowledge by retraining the model weights on new data. It is expensive, highly time-consuming, and computationally intensive, requiring massive resources. Furthermore, if you need to update that information, you must undergo another costly and time-consuming fine-tuning run, making it difficult to keep pace with quickly changing corporate data. And critically, the results are a black box, lacking transparency and auditability, making it impossible to trace the origin of a generated statement. RAG, conversely, is the clean investigation. It leaves the core LLM untouched, using it only for its sophisticated reasoning and synthesis capabilities. This makes RAG fast and highly cost-effective. Updating information is simple and instant. You just add the new document to the knowledge base, vectorize it, and the data is immediately available to the retriever. Most importantly, RAG provides auditable and citable answers. Because the answers are grounded directly in the retrieved sources, you always have a complete chain of custody, ensuring trust and full transparency traced back to the original evidence. To conclude our investigative journey, let's quickly recap the entire RAG pipeline, bringing our case file to a close. RAG is not a new model itself. It is a sophisticated system, an investigative framework that wraps around any powerful large language model, ensuring its brilliant mind is never detached from the facts. It brings order to the chaos of potential hallucination. Our process starts at step 1, the crime scene, which is the raw data in the knowledge base. This is processed in step 2 by forensics, the embedding model, which turns text into numerical vectors. These vectors are then stored and indexed for rapid retrieval in step 3, the evidence locker, or the vector database, utilizing techniques like HNSW. When a user submits a query, it triggers step 4, the warrant, which is executed by the retriever. The retriever uses the query to pull the most relevant chunks of evidence, essentially creating a summary of all relevant facts. Finally, in step 5, this evidence is used to augment the prompt, forcing the generator to produce the verdict. The result is the truthful, grounded answer. The error 504 is a gateway timeout. To resolve, restart the engine X service. This answer is accompanied by precise references, confirming that every assertion is backed by verifiable documents. File A and File C RAG is the crucial mechanism that enables reliable, verifiable, and responsible AI deployment, transforming powerful but static LLMs into trustworthy tools for enterprise knowledge.